Welcome back to part 2 of this Commodore SuperPET repair. I'm recording from the future as I had a mishap with my old project files, but I'm back with the original video, maybe a little less context than I was hoping for. This will probably still make sense if you haven't watched part 1, but last time we went over a SuperPET that wouldn't boot. We took it apart and used a ROMulator to show that many of the components of the SuperPET are working just fine. In fact, it seems like there's a memory problem at work here. So, here we go. Okay, what I'm trying to do now is get an idea of our memory layout here. So on the PET, we've got a lower RAM block and upper RAM block. The address lines are these three TTL chips, all LS244s. So what I'm going to do first is just check our inputs and see how our selects are happening. These are UE 8, 9, and 10. So UE8, G1 is pin 1, G2 is pin 19. Let's just start with 1. UE8 pin 1. Okay, that looks normal. UE9. That took a second, but that looks normal. UE10. UE10 is high. Some ripple, but it's high. UE10 is coming from UE5, pin 11. 7, 8, 9, 10, 11. That matches. So it's a 74LS00. So 11, 12, and 13. 11, 12. So it just bottomed out. Mux A is on page 6. Mux A is coming from Y3 on an LS157. That is UE2. It's all the way down here. And 9 on UE2. That's low. So Y3 is going to come from 3A and 3B. Has a good signal. 11. Okay. So on a 2 to 1, a 157 would be an enable low. Though both of those are active, then it should be doing something. S is high, and that's fine. So 15 is high. So this isn't even being enabled. So it has nothing to do with any of those chips, really, because we're going back from there. So following this back, we got an LS10 at UD4, pin 8. It's also high. An LS10, I don't know what an LS10 does, but given that it's 3, I'm sure it's like a NAND, 3 to 1 NAND, so any of those are low, then it's going to come up high. So if I go to UD4 again, UD4 and it's 8, so 9, 10, 11. 9 is low. 10 is low. 11 is low. So our address lines are low. So UD1, pin 4 is low. 5 is low. 6 is middling. So BA14, LSO2, see jumper table below. Oh, sure. So you've got W and you've got Z. Either way, BA14, BA13. Where's BA14 coming from? BA14, so AB14 is 24, comes into this LS244 at 15, and comes out at 5. All right. So UD14 in at 15, out at 5. So what does 5 look like? Five is high. So it's high coming out of here. Do I have this right? Okay, so after a while it dies out, but that's a signal. So 5 goes down to, so it goes off to page 6, and it also goes off to 16 on the memory expansion bus. 24, 23, 22, 21, 20, 19, 18, 17, 16. Okay, that's okay. It's not dragging anything down. And then we need page 6. Okay, we saw that. BA14. Does it go anywhere else? 3A. 3B. Mux A comes from page 6. Mux A comes from 9, comes in from 3A and 3B. 3A and 3B. Right, okay. So 15 goes back to UD4. And then UD1. BA14 comes into Y. Y is going to be dead. The 74 LSO2. On our schematic, 5, 6 goes to 4. 2Y, 2A. 2A and 2B go to 2Y. So this is a positive NOR gate. So 1, 2, 3, 4. Nothing. 5, 6. 6 should be on Z. Oh, that's gonna be a problem. Right there. Cool. Unbelievable. That is 100% the problem. Is that stupid little jumper. There it is. Let me reconnect the display. Make sure we see all of our RAM, because now that we can access it, hit a start. The monitor disconnected, but this is not what a video signal looks like. My horizontal pulse is 12 Hertz. My vertical pulse is 5.8 kilohertz, so that's not going to work. So the initial ROM is initializing, and so we get the chirp, but then nothing. So we're not even getting the CRTC properly initialized. It seems like it's trying to. So what I'm thinking from here is I'm going to start checking signal to the RAM chips. We have VBB on 1, VSS on 16, VCC on 9. So looking on pin 1, -5, and it is, but that is minus 6.5 volts. That's a volt and a half off. VCC should be 5 volts. That's 5.04, so that's just fine. VDD on 8 is 12 volts, and that's 10.4. Well, I was hoping to do this without pulling this board. One of these voltage regulators are what take our inputs and provide the -5 and 12. And if I were to look at our schematic, -5 volt comes out of VR1, plus 12 comes out of VR2, plus 5 comes out of VR4, and another plus 5 comes out of VR3. Okay, that is -6.5 out of VR1. No, it's VR1 that's dead. VR1 is the one sending out -10.8 because it's generating -5 out of that. Okay. Alright. Cool. Now I think I'm gonna need a keyboard. So right now my theory is that this is an addressing problem. Pet tester is weirdly showing @ signs everywhere, which looks like a 00 byte being overwritten into whatever it's displaying with. When I try to load software, the program corrupts itself, but it's getting somewhere. So I don't feel like it's a data bit problem. It could be, but I'm going to start with addressing because that's the part that makes the most sense. So on the schematic here, my address lines from 0 through 15 here go through UD13 and UD14, which are LS244 chips. That creates the buffered address bus, which then goes, throughout the whole machine. So we'll start there, I think. So I'm going to scope out. I'm going to start the 6502 with the no-op generator. I'm going to go through and just look at the input and output of the buffers on UD13 and UD14 just to see if I'm getting a good square wave and if the square wave seems to have the right voltages for good TTL values. So I'm going to start it up. We're going to start at UD13 pin 17. So decent square wave, maximum of 4 volts, which is doable. Comes out 3. I don't know if that's coming through on the camera. Maybe I'll try to save an image. It looks wobbly, for lack of a better term. It's still doing a maximum of 4. It is coming down to 0, so that may be nothing. It just looks off to me. Let's try 15. 15 is a good solid square, 3.92, 4.0 volts. 5. So again, kind of wobbly. Now, that could be something on the other side being driven improperly. I'm going to do one more here, 13. 13, another pretty solid 4 volts. That's coming out on 7, 8, 9. So again, wobbly. How's our 5 volts look on here? I assume 5 volts is coming in on 20. Yep, that's fine. Okay, so if I look at UD14, which is handling A8 on up, if I look at, we start at pin 8, it's our input, it looks pretty normal, coming out at 12. It's got a little bit of that wobble as well, but not nearly to the level that I was seeing before. But let's let's try the next one. 8 goes to 6. 6 looks good. Comes out on 14. Yeah, that looks nice. So I don't know enough about 244s to know for sure, but that output looks extremely weird. And just for grins, let's just look at another 244 in that same kind of, it's like, let's look over here at UE8, right? 20, 19, 18, 17, 18, right? 17. So that's an input, and that looks normal. It's actually better than the one before. So I guess that's being driven by something great. And 17 would come out at 3. So if I go over to 3, does it still have that weird wobble? Well, there's a lot more going on that bus. But the square waves look better. That's interesting. Can you piggyback a TTL chip? I know it's questionable even with RAM, but you're just looking for differences, right? See if something different pops up. What happens if you piggyback? I'm sure it's not the same. But just before I start tearing into it, why not? Why not try it? So we're back on UD13. Pin 17 on a piggyback chip. 20, 19, 18, 17. Still got a good solid square wave. Obviously there's wobble there. I don't think it does anything, honestly. Just for grins, I'm just going to switch this back to the standard ROM and just panning over to our screen. Okay, so that's interesting, right? So I'm still running through the ROMulator, and I don't know if it's going to bother picking up the upper bank or not. We'll have to figure that out in a second. But it isn't 5K bytes free. It's like a 16K RAM machine, right? I mean, that's a huge change. I think that might be our IC. And if we change that out, this might work a little better. So we definitely still have memory issues. Okay, so I am going to steal an idea from Adrian's digital basement. One thing that he did is had a very simple basic program to just push some values into memory. If we're getting this corruption, I think it's similar to something that he ran into with his 4032. So I'm going to try the same thing. The first thing I'm going to do is I want to take a look at the start of basic memory. So we got a little bit of values here, and otherwise we're all A's here, right? So let's do this program. So what this program does is starting at 1280, we're pushing in a value and doing that all the way up 4K. we're going to run this program. Oh wait, no, first, let's look at the program. So now we have this program. Let's run this program. Syntax error in 10, right? So the program corrupted itself. I'm going to list it in a second, but we're going to be able to see with this memory location. The syntax error doesn't exist. Watch. So won't be able to see it very easily on video. 001D turned to 1C. 81 turned to 80. 49 turned to 48. So if I X out of this, and I list the program, my 4 turned into an end, my I turned into an H, my 4096 turned to 4086, my poke turned into a define. So after running those two side by side, I took the pictures that I took of the screens and just mapped them in this file so we could do a little difference check. So on line 1 is the run, or is the memory map of 400 before we ran the program, and 2 is after, so after it had a chance to corrupt its own memory. By having these side by side, we'll be able to figure out the difference between the two in binary, hopefully determine how many of these chips might need to be changed. At the very least, we can see what might be affecting things around it. If we have crosstalk, if we have a bad chip, what's going on. So first line at address 0400, we have 1F versus 1E. So 1F is 1111. 1E is 1110. So the very first bit flipped, creating that difference. And do we have any others? We have 81 and 00, which is, of course, 0000. And 81 is 0001, although there is an upper bound difference of 1000, 0000. 49, 1001, 48, 1000. So we're gonna have to keep an eye on this. That could be relevant here. So on this set, what are our differences? Looks like we have 39 and 38. Again, one off. So that's a good sign. We might still be pointing at the same one. 1001. And anybody watching has already calculated this, because why on earth do I need to use the calculator for binary? But, oh well. Down here we have, again, one different. 1, or 0111. 96, I'm going to guess is 0110. Yep. So again, first data line, our first bit, everything else matches here. And then down here, we've matched completely. So at the very least, we have this first bit that changes. The other potential issue is our 8th bit might also be changing. So that's something we might want to consider. But in the meantime, we kind of have our order of operations here. So if we have the first data bit, if we walk over to our schematic, we have our RAM page here. And on Commodore schematics of this era, it kind of gets a little easier because we can find our data bit and make a determination. So our first bit is D0. So we follow this up and we land on UA19. UA19 is the very first chip on the board, closest to the rear of the case. If we need to go all the way back, it's possible that D7 is messed up because we saw that one change. Now that's the case. That is UA5, which of course we end up almost to the bottom. Now D0 also maps up into the upper bank up here at UA18, and D17 is also up at UA4, but I don't think we're touching that RAM, and because we're not having a bus conflict necessarily, I'm not going to touch these until I know. Now we aren't detecting all of our RAM, and so we're going to have to maybe attack this later, but let's do one at a time. Let's not preemptively do stuff. So I'm going to start with UA19, and then we're going to recheck. Truth. Well, that's a good sign. I mean, not necessarily. This is supposed to be a 32K RAM machine, but this is without the ROMulator, so that's good. So why don't we try the program from before. Well, no syntax error. That's a good start. Let's see if we can load stuff from the disk. No corruption. Well, the camera hates this a lot, but the 16K RAM test says okay. Display RAM test, ROM test. What's interesting is that this is also saying that we have 16K of RAM. This is a good start. Reversal board. Y and Z control 16K or 32K. Y is 16K, Z is 32K. And Z is solidly connected here. So let's take a look here at our RAM. So we have our lower RAM block and our upper RAM block. So the address lines are the same. They're all coming in from this here. So it looks like pins 18 and 16 out of UE8 come over to address line 0 and 1 on the upper bank. RAS 0 feeds both the upper bank and lower, but CAS 0 goes to lower and 1 goes to upper. So what I'm going to look for is I'm going to look at pins 18 and 16. I'm just going to look at pin 15 on UA4 just as a starting point. So pin 15 is basically high. there's movement, there's obvious movement, but it's basically high. If I go and I look at UE8, 16, those seem fine. And I would imagine they would be, because that should affect UE10 as well, which would affect the lower block. So going back to CAS 1, and maybe that just stays high because we're not touching the upper bank anymore. CAS 1 comes from UD5 pin 11. Still high. Which is fed from 12 and 13. This is a 74 LS00. So this is the 4th gate, and A and B feed Y. An output of high would either be A is low and B anything, or B is low and A is anything. So I think from this point, I think I might grab the logic analyzer. If A is high, or if A is low and B is anything, it should be high. And if B is low and A is anything, it should be high. A low, B low, high. A high, B low, high. So the only way this will go low is if both are high. And at no point are they both high. Okay. So there's an LS137, a quad 2-to-1 mux at UE2, which is fed by this LS164. So 82 is 01010010. 210 is 11010010. So it looks like our 8th bit, or D7, is the problem. D7 is UA5 and UA4. So maybe UA4 is our problem?
Yes! Yes! Yes!
It does not get better. 32K of RAM detected okay up top. Display RAM checks out. The ROMs check out. The 8032 side of this thing is checking out fine. I'm going to have to see how broken the 6809 side is. Let's get that board in. Okay, we still have a boot, still have 32K of RAM. So I'll shut it off. And then forward should be 6809. And let's see if we have more repairs to do. No noise. Cool. Now what's weird is that the RS-232 port is inside, so I guess if you had that running, you'd snake it in and then probably send it out the side here and have it going somewhere else. I'll probably need a disk. Yeah. Well, this thing works, at least as far as I have it today. I have some disks to prep, but I'm going to save that for another time. Thanks for watching on this adventure, and I'll see you next time.